And today's 7-syllable word is eigendecomposition. Yikes, what is that? Essentially, it is a special case of another 7-syllable concept that we discussed in the previous video, namely diagonalization. So to really understand eigendecomposition, we need to first take a step back and dwell on diagonalization a bit. So let's begin by recalling a few facts from the previous video. To diagonalize a linear map T is to represent T as a matrix relative to some well-chosen basis B, so that T's matrix representation relative to B is a diagonal matrix. And what we saw last time was that the way to do this, the way to find that well-chosen basis B, is to use an eigenbasis relative to the map. If we can find such an eigenbasis, then the matrix representation of the map relative to it will be diagonal. And if there is no such eigenbasis, the map cannot be diagonalized. Let's briefly remind ourselves why an eigenbasis is so crucial here, because bearing that in mind will help us understand the underlying geometry and give us better intuition for what's going on with diagonalization, which will serve us very well when we talk about the very specific case of eigendecomposition. So let's say we have a linear map T that maps R3 to itself. And let's say we are so fortunate that we do have an eigenbasis of R3 relative to this map. That would mean that I have 3 linearly independent vectors, I'll call them B1, B2, and B3, that are simply scaled by the linear map. And for the sake of illustration, let's suppose that B1 is scaled by a factor of 5, B2 is scaled by a factor of 3, and B3 is scaled by a factor of -2. And that's what happens to the vectors in our eigenbasis B. Well, in that case, it's easy enough to write down the matrix representation of our map relative to the eigenbasis B. Back in chapter 6, we learned that the columns of this matrix are the images of the basis vectors expressed in B coordinates. And it is precisely the fact that the 3 eigenbasis vectors are simply being scaled by the map that is going to turn this into a diagonal matrix, because it means that every column is only going to have one non-zero entry, and those entries will always be on the main diagonal. For example, the first column, which is the image of B1 in B coordinates, what will that be? Well, the image of B1 is 5B1. So to express 5B1 in B coordinates is simply to ask how many B1, B2, and B3 steps do I have to take to get to 5B1? Well, that's obvious. To get to 5B1, I take 5 B1 steps, and then I'm there. So I don't have to take any B2 steps or B3 steps. And all looks well. The same story plays out in the other columns. The second column, which consists of the B coordinates of the image of the second basis vector, well, the image of the second basis vector is 3B2. So how many B1, B2, and B3 steps must I take to get to 3B2? Well, obviously, we take 3 B2 steps and none in the other directions. Same story for the last column. How many B1, B2, and B3 steps must I take to get to -2 B3? Well, obviously, we take -2 B3 steps and none of the other sort. And lo and behold, there is our diagonal matrix. So we have indeed diagonalized our linear map. We found a basis, a well-chosen basis, namely an eigenbasis, such that representing the map according to that basis gave us a diagonal matrix. And you can see, of course, that the entries on the diagonal are simply the eigenvalues of the eigenvectors in the basis. And thinking about the map relative to this eigenbasis shows us the essence of the map itself, because, as we saw last time, each one of these eigenvectors in the eigenbasis lies in an eigenspace, and every vector in each eigenspace is an eigenvector with the same eigenvalue. In this case, the eigenspaces are necessarily one-dimensional, and we could think of them as representing the intrinsic axes in some ways, the right axes to look at in R3 when we're thinking about this map. What this map does is stretches vectors or components of vectors along those 3 axes, and that's it. So to know what happens to any given vector in R3, well, we think about its components relative to the eigenbasis. Those components get stretched and then added back together, and that's where that vector will get mapped by t. Okay, good. So geometrically, we like an eigenbasis because it shows us what's going on with a map in a very simple sense. It breaks it down into a collection of mere scalings along axes. But as I've said 1,000 times in the course of this video series, in linear algebra, we want to keep going back and forth between the geometric side of things and the algebraic side of things. And here, the algebraic side of things is all about these diagonal matrices. And we really like diagonal matrices. They have nice algebraic properties. I mentioned this briefly in the last video, but I want to say a bit more about it now because having those in the back of our mind will help us appreciate eigendecomposition when we get to it that much more. So for a moment, let's forget all about the linear map and the geometric side of things and just think about this diagonal matrix. I am going to rename it D, and it is going to stand here for any diagonal matrix. There's nothing special about this one. We could be considering an 8 by 8 diagonal matrix or a 20 by 20 or a million by million. Doesn't matter. Anyway, the first thing I want to show is that if we do some sort of matrix vector multiplication, where the matrix involved is diagonal, then compared to matrix vector multiplication, where the matrix is just any old matrix with nothing special about it, the one involving the diagonal matrix involves far fewer computations, which is not too surprising, thanks to the presence of all of those zeros. And this is an important point in any computer science setting, or anywhere where somebody is writing a program to carry something out, because the fewer computations are involved, the more efficient the program will be. And to emphasize this point, let's actually try to work out how many arithmetic operations are required to carry out matrix vector multiplication in general versus how many operations are required to carry out matrix vector multiplication when our matrix is a diagonal matrix. Let's think about it over in this corner of the screen. Let's just consider a square matrix, an n by n matrix. So the vector would have to be one with n components. So this is our matrix A, this is our vector V. And when we do this multiplication, of course, we end up with another vector with n components, and each one of those components, let's concentrate on the first one, is a dot product of a row of the matrix and the vector itself. And each such dot product is going to entail n multiplications, the product of the first components, the second components, the third components, all the way down to the nth components. And then the results of those multiplications have to be added up. And since there are n things to be added together, that will require n minus 1 additions. After all, if you're adding 2 things together, that takes 1 addition. If you're adding 3 things together, that takes 2 additions. First you add the first 2, then you add the third to the sum you already found. So anyway, to get one component of our output requires n plus n minus 1 operations, n multiplications and n minus 1 additions. Put all that together and we have 2n minus 1 operations. But that is just for the first component. We have to do that n times once for each component. So the entire process of matrix vector multiplication, where we're using any old n by n matrix, requires n times 2n minus 1 basic arithmetic operations. And let's distribute that n and rewrite it as 2n squared minus n operations. In contrast, if our matrix is diagonal, like so, life is going to be much easier. In fact, this will be easier to see if instead of just calling this matrix D, I make the diagonal entries D1, D2, all the way down to Dn, and of course we have zeros elsewhere. By the way, often when discussing a diagonal matrix, we do just write the entries on the main diagonal and leave the rest blank, so we do not have to devote precious minutes of our life to filling in lots of zeros. Anyway, let me do the same thing with this vector, rewriting it as v sub 1, v sub 2, all the way down to v sub n. Writing it out this way will help us see what is going on better. Once again, let's think about what is involved in computing the first entry. Well, exactly as we said before, we're going to take a dot product of the first row and the vector, but we don't actually have to do all the multiplications, because except in the first one, we will always be doing a multiplication where it's 0 times something, and those all turn out to be 0, so they contribute nothing to the sum. So we actually only have to do one multiplication, d1 times v1, and we need not bother with the rest of the terms in the dot product because they're all 0, and then there's nothing to add up. So this guy only requires one operation, a single multiplication. And of course, the same thing is going to be true for the second component, because when we're looking at the dot product of the second row and the vector, we only only have to consider one multiplication, d2 times v2, because all the other products we know have to be zeros. And so again, there's nothing to add up. And the same is true for all n components, which means that overall, to do the matrix vector multiplication, when we're working with a diagonal matrix, we only need n basic arithmetic operations. And you might say, well, n, 2n squared minus n, what's the big deal? Are they really that different? Sure they are. These grow at totally different rates. The one is growing linearly, the other is growing quadratically. Even when n is small, there's a substantial difference. When n is 3, if we're working with a 3 by 3 matrix, if it's diagonal, then multiplying by a vector only requires 3 operations. If it's a general 3 by 3 matrix, that's going to require, what is that? 15 operations. We all like to be lazy, and having to do only 3 things is nicer than doing 15 things. But the real payoff is when n is large, as it so often is in applications. Even if n is modest, like 100, then this sort of multiplication requires 100 operations, whereas this sort requires, what would that be? Almost 20,000 operations. 19,900 to be exact. And if n is 1,000, if we're working with 1,000 by 1,000 matrices, in the one case, with a diagonal matrix, we have only 1,000 operations to do. With the non-diagonal matrix, we have almost 2 million operations to do. Of course, you and I aren't going to do those operations by hand, even with 1,000, but our computers will. And our computers are much happier doing 1,000 things than doing 2 million things. They can do the 2 million things, but it's going to require a lot more time and slow them down, which we don't like. Good. But lest we get lost in questions of computational efficiency, just come back to what's involved. Multiplying a diagonal matrix and a vector is as easy as could be. To write down the product in this case, the first entry would just be d1, v1, the product of those two entries. The second entry is simply d2, v2, and so on all the way down. So for example, if I took a specific diagonal matrix and multiply it by some specific vector, I can write down the product basically as fast as I can write. It couldn't be any easier. But the blessings of working with diagonal matrices are not confined to matrix vector multiplication. It works with matrix multiplication as well. If we have some matrix B, n by n, and we multiply that matrix on the left by, on the one hand, a perfectly ordinary matrix A, and on the other, a diagonal matrix D, then the multiplication with the diagonal matrix will once again require far fewer computations, far fewer basic arithmetic operations to carry out. Let's come over into this corner again and figure out how many fewer. First, consider the general case, A times B, where A and B are just any old square matrices, n by n. The product is now going to be another n by n matrix, and this will be easiest to analyze if we take the column perspective on matrix multiplication. And in fact, to do that, let me take this matrix B and label its individual columns B1, B2, all the way down to Bn. According to the column perspective, the product of these two matrices will have as its columns A times column B1, then A times column B2, all the way down to A times column Bn. And we know that to get any such column, say the first, well, if that's simply a matrix vector multiplication, we already know from our earlier work that getting each individual column will require 2n squared minus n operations. We'll need to do that not just once, but n times once for each column. So that means the overall process of multiplying those two square matrices together requires n times 2n squared minus n operations. Or in other words, 2n cubed minus n squared operations. So now we've got something that's growing like a cubic. This will get very big very fast. How about our simpler case where the matrix on the left is diagonal? Well, in that case, we can carry out the same analysis with the column perspective on matrix multiplication, except now producing each column is a matter of matrix vector multiplication where the matrix is diagonal. And we already know each one of those only requires n operations. So n operations for the first, n operations for the second column, all the way down, n times, which means that overall we will have n times n operations needed to carry this out. So this sort of multiplication requires only n squared operations. That's much better than the general case. If we're working with 100 by 100 matrices, then if the left matrix is diagonal, we only need 100 squared, 10,000 operations, which might sound like a lot, but not when you compare it to this case, which would require nearly 2 million operations. operations. 2 million minus 10,000. So 1,990,000 operations. Clearly, your computer will be much happier computing this one if it can. And now let's consider a very special case of matrix multiplication. Namely, when we are multiplying a matrix by itself. Either a general matrix multiplied by itself, A times A, or a diagonal matrix multiplied by itself, D times D. Or as we might write these a little more simply, A squared and D squared. Well, squaring a general matrix still requires the same number of operations as multiplying it by some other square matrix, namely 2n cubed minus n squared of them. But squaring a diagonal matrix is especially simple, because now we have lots of zeros not only in the left matrix, but on the right matrix as well. And in fact, it's not hard to see that when you square a diagonal matrix, the result is yet another diagonal matrix whose entries on the main diagonal are simply the squares of the main diagonal's entries on the original matrix. I will leave it to you to convince yourself that that is so. You can do it by using the same kind of arguments we've been doing for the last few minutes, but that means that squaring a diagonal matrix really only requires n operations, one for each entry. For instance, if we square this diagonal matrix, whose diagonal entries are 5, 3, and minus 2, we get a new diagonal matrix whose entries are 25, 9, and 4. And that's that. Only 3 operations involved rather than the 45 operations that would be involved in squaring a general 3 by 3 matrix. And of course, if we are working with a large matrix, then the savings are really substantial. Squaring a 1,000 by 1,000 diagonal matrix only requires 1,000 operations. Squaring a 1,000 by 1,000 general matrix requires almost 2 billion operations. So yes, we like diagonal matrices very much. And maybe the last thing I will say here, because we will come back to it towards the end of this video, is that when we are considering the problem not merely of squaring a matrix, but of raising a matrix to some higher power, k, the 10th power, 50th power, or 100th power, then these differences become even more magnified. Raising a general matrix to some higher power k, well, let's just say it requires a lot of operations. But raising a diagonal matrix to the power of k is easy. All you have to do is raise each one of its entries to the kth power, which is a piece of cake. And as I said a moment ago, we will see this sort of thing again very soon. But a very reasonable question you might ask here is, okay, that's all very nice, but really, this seems like a very exotic operation. Why would we ever want to take some matrix and raise it to the 200th power or whatever? I mean, maybe it's interesting that this is much, much easier if the matrix is diagonal, but does it matter? Yes, it does matter. Why? Well, consider this. As we have been discussing since chapter 3, we know that we can think of any matrix as a representation of a linear transformation. And if it's a square matrix, like let's just say this is a 3 by 3 matrix, then it represents a linear transformation of a space into itself. Like a 3 by 3 matrix represents a linear transformation of R3 into R3. It simply takes the vectors in that space and moves them to new locations. Or if we like, instead of moving vectors around in space, we can think of the underlying linear transformation as moving points around in space. Now, many applications of linear algebra involve iterative procedures where we start with one point, transform it in such a way that it becomes another point, transform that again by using the same map into a third point, and then we transform that output to get yet another, and so on and so forth. And typically we are concerned with things like what happens to that point in the limit as we keep iterating the matrix multiplication, or equivalently iterating the linear map that underlies that matrix. This, I am told, lies at the heart, for example, of many, if not most, linear algebraic applications in machine learning. But at any rate, look at the successive outputs in this procedure. We go from V to AV to AAV, better known as A squared V, and then to A times A times A times V, better known as A cubed V, and so on and so forth. The next few iterations would be A to the 4th V, A to the 5th V, A to the 6th V. So it's not at all unreasonable to ask, well, where is the point after 200 iterations? That would be at A to the 200th power times V. If A is just some general square matrix, especially if it's a large square matrix, not just a 3 by 3 one, then computing this might seem hopeless, even for a very fast computer. But if instead we have a diagonal matrix, then computing this is child's play. All we have to do to get d to the 200th power is raise those diagonal entries to the 200th power, and then it's just a single matrix vector multiplication, which itself is especially easy because d to the 200th is still diagonal. All this is to say that there are very, very good reasons why we like to diagonalize linear maps. We like our matrix representations to be diagonal when that is possible. Now, that's not always possible. We have to have an eigenbasis relative to the map, but when we do have one and we can get a diagonal representation, we are very happy because we can do things that otherwise we would not be able to do. Okay, I'm guessing I have now convinced you of the virtues of diagonal matrices. We know exactly what it is we need in order to diagonalize a linear map, namely an eigenbasis, and we know why we would like to do that in the first place. We still haven't even talked about the problem of how do we go about finding an eigenbasis, but you'll know how to do that by the end of the next lecture. Those are just technical computational details. I'm concentrating here on the big ideas because those are the things you don't want to lose sight of. Now, there's one more thing we need to talk about having to do with diagonalization before we reach the specifics of eigendecomposition. And once you understand it, then the step to eigendecomposition will be very simple and very natural. We've now spent quite a bit of time talking about what it means to diagonalize a linear map. But a linear map is a kind of abstract, ethereal object. Like we can imagine, here is our linear map T floating about in the ether. Wonderful, coordinate-free, immaculate, and so forth. But down here on Earth, what we encounter in many applications are simply matrices, grubby boxes of numbers, wretched pale shadows of the thing itself, the Platonic form, if you will, a linear map, pure and free of all this mundane tawdriness. So in practice, we might have our eyes fixed on some particular concrete matrix, and the problem for us is not to diagonalize a linear map in its purity. In other words, to project it down onto Earth into some nice diagonal form that represents it. The problem for us is to look at our earthly matrix, recognize, but nonetheless, this matrix can be viewed as a representation of some linear map, a linear map that could be represented in many other ways, and we want to find, if at all possible, one of these other ways it might be represented so that it will appear on Earth as a diagonal matrix, a kind of brother to the given matrix, different on the surface, but representing the same underlying linear map. And then we will say, if we can do it, that we have successfully diagonalized this matrix, as opposed to diagonalized this map. It's ultimately the same thing, but there's one extra little mental maneuver. So let's jot down a few notes on this process. To diagonalize a given matrix A is to think of that matrix A as the standard representation of T, where T is a linear map, and then to find an eigenbasis B relative to that map so that T's representation relative to the eigenbasis is a diagonal matrix. As I said a moment ago, this is really the same thing as what we were talking about up here, just with a little extra mental maneuver. And if you understand this concept, then eigendecomposition is going to be a piece of cake for you, because the process of diagonalizing a matrix actually produces the eigendecomposition as a kind of byproduct. But before we dig into any details, I want to return to my image of a linear map T in all its purity and its earthly matrix representations. If T is a map from a space to itself, then different choices of bases for that space yield different matrix representations of the map. So if we use the standard basis E, for example, then the map is represented as some specific square matrix, some specific box of numbers. Whereas, if we used basis B, then our map would be represented as some very different looking square matrix, some other box of numbers. And if you encountered these two matrices on the road, you probably would not be able to tell by looking at the specific numbers they contain that they are under the skin, brothers, as I described them earlier, and yet they would be. Matrices that are related in this way have important deeper properties in common, and the official, if not particularly descriptive term for such matrices is that they are similar matrices. And it is important to understand that there are two different views of similar matrices that we can take. They are equivalent, but like so many other things in linear algebra, we want to be able to shift perspectives frequently and think of the same object in many different ways. So the first thing to bear in mind about similar matrices is what we have said already. They represent the same linear map, just relative to different bases. To use our analogy from Chapter 6, they are describing the same object, albeit in two different languages, B and E, or whatever the bases are. That is really the fundamental idea of similar matrices. That's why we care about them. But there is a second, purely algebraic view of similar matrices that is very important as well. The equivalent algebraic condition is that square matrices M and N are similar if we can surround one of them with some third matrix and the inverse of that third matrix, and the resulting product will be the other matrix, other of the original M and N, I mean. So for example, we might have that if we start with the matrix M, and by surrounding it by some other matrix and its inverse, I mean that we could hit M on the left, say with some matrix C, and on the right with the inverse of that matrix, C inverse, and if that product turns out to be equal to N, then that would mean that matrices M and N are similar, according to this algebraic condition. And the reason I wrote it out rhetorically like this, rather than something like this, is to make it clear that it doesn't matter which one of the surrounding matrices has the inverse sign. I mean, they are inverses of one another. We could just as easily call C inverse the matrix, and then its inverse, C inverse inverse, would be C. So this would be a sign that M and N are similar according to this criterion, but it would also work if we showed that, say, M was equal to P inverse times N times P for some matrix P. Either way, we've taken one of the matrices and surrounded it with a third matrix and its inverse, and the result was the other matrix that we were starting with. Okay, fine. But it's not obvious why matrices that stand in such a relationship to one another actually represent the same linear map relative to different bases. So we need to explain why that is so. So we want to understand why the algebraic condition implies this fundamental notion of similarity. I'm going to need a little more room to explain this, so I will make myself a little room. There are really two little insights we need here to help us understand why this works. First insight, every n by n matrix can be viewed as the standard representation of T for some linear map T. Now, this is actually completely obvious. We've been doing this since Chapter 3, and all I mean by this is that if we have some random, let's say, 3 by 3 matrix, like, say, 3, 1, 4, 1, 5, 9, 2, 6, 5, then even though I just wrote this down as a box of 9 numbers, with no thought of any geometry or any particular application in which this might arise, I just threw some numbers in the box. Nonetheless, I can think of this thing as representing a linear map in standard coordinates. Obviously, we've been doing this for a long time. Namely, this is the standard representation of the map on R3 that sends I hat to 3, 1, 2, sends J hat, the second standard basis vector, to 1, 5, 6, and sends K hat to 4, 9, 5. It moves I hat, J hat, and K hat to those 3 new locations and drags the whole grid along with it, and that's our linear map T. Obviously, we can do that with any matrix whatsoever. We don't even need the matrix to be square. I just threw that in there because we're dealing exclusively with square matrices in this particular video. Okay, so far so simple. What is the second simple insight that we'll need to explain the equivalence of these two statements about similarity? Well, this is going to be a statement about every invertible matrix. Maybe not a surprise that we're going to talk about such things, since our algebraic condition for similarity involves a matrix and its inverse. But anyway, every invertible matrix can be viewed as a B to E change of basis matrix for some basis B. Now, why is that so? Well, a numerical example will help. Here's a 3 by 3 invertible matrix. How do I know it's invertible? Well, a few moments of staring at it and thinking about it should convince you that the columns are linearly independent. And we know if we have 3 linearly independent columns, then our 3 by 3 matrix must be invertible. That is from everyone's favorite theorem, the invertible matrix theorem. Okay, so it's invertible. But why can I think of it as a change of basis matrix from some mysterious basis B to the standard basis? What would this mysterious basis B be? Well, it's staring at you in the face. Our columns, these 3 linearly independent vectors in R3, of course, constitute a basis for R3. And if we imagine these, as we naturally do, as the standard coordinates for these 3 vectors, then we could say that the columns are the standard coordinates of the 3 vectors in some basis B. And that's exactly how you form a B to E change of basis matrix. The first column is the first basis vector's standard coordinates, the second column is the second basis vector's standard coordinates, and the third column is the third basis vector's standard coordinates. So sure, this is the matrix that changes from B coordinates to E coordinates. Okay, simple enough. This is a way of viewing any matrix. This is a way we can view invertible matrices. We don't always have to think of them this way. We often don't. But if it's convenient, we can do it. And it will be very convenient in explaining why this weird algebraic condition implies this fundamental meaning of similar matrices. So, to that end, suppose this condition holds for a pair of matrices M and N. So let's say M is what we get if we take N and surround it with C and its inverse, like that. C inverse NC. Well, why on earth should this algebraic condition tell me that M and N actually represent the same linear map relative to 2 different bases? Well, this is where our 2 little insights will help us. Let's look at the right-hand side of our equation and think about the individual factors. Let's start in the middle with that matrix N. N is just some square matrix. So I'm going to view it as the standard representation of some linear map T. So let me go ahead and write that underneath, like so. Now, surrounding that matrix, I have some matrix C and its inverse. Oh, so I'm dealing with an invertible matrix. Otherwise, I couldn't talk about its inverse. So that means my matrix C is something that I could view as a change of basis matrix from some basis to the standard basis. So let me go ahead and write that down below as well. I'm just using my usual bookkeeping shorthand here, reminding me that what C does is to convert from basis B to basis E. And if that's what C does, well then of course I know what C inverse does. Being the inverse, it inverts this conversion, and instead of going from B to E, it goes from E to B. Good. Now thinking about these 3 factors in this way allows us to see what's going on just by following all these little subscripts. Remember, of course, we're reading from right to left, like function composition, which is what matrix multiplication is. So how does this product work? Well, we are going to feed in some vector V's B coordinates, because that's what the rightmost matrix likes to eat, B coordinates. So we feed that in. We can always think of any stack of numbers as the B coordinates of some vector V. We feed it in. The first matrix it encounters changes the vector's B coordinates to E coordinates, and it passes the results on to the second matrix, which takes those E coordinates, transforms the underlying vector, and returns not V, but TV, the image of the original vector, but expressed in standard E coordinates. Okay, so what comes out of this one are the standard coordinates of T of V, and then it encounters the C inverse matrix. And what does it do? It takes the E coordinates of our vector T of V and transforms them into B coordinates. So what comes out of this mess is the B coordinates of T of V. So now we just have to think about the net effect. What overall has happened? Well, we started with the B coordinates of some vector V, ran it through all this stuff, and we ended up with the B coordinates of that vector's image under T. So what did this matrix product, which is this matrix product, actually do? Well, it simply carried out the linear map T relative to the basis B. So that means that this matrix product, at the end of the day, is the representation of T relative to basis B. But of course, this product, which is this product, is also matrix M. So that means that our matrices M and N really can be viewed as 2 different representations of the same linear map T, albeit relative to different bases. So this is a sensible algebraic condition indicating that two matrices are similar in the real, true, deep sense of similarity, the reason why we care about similarity. Good. So now we know why. So along with all that other stuff, I can get rid of that question because now we know the answer. All right. And with that, I think it is time to look at our first eigendecomposition. So long ago, way back in elementary school, you learned that when we have some whole number, like say 6, we can often factor it into a product of simpler and more fundamental numbers. Like here, where we have 6 is 2 times 3. This prime factorization exposes something essential about the number 6. These are the multiplicative atoms from which it is built up. And this is so familiar to you now that you don't think much of it, but it can help us here to think of this as a kind of decomposition of the number 6 into a product of revealing factors. And that was not the only time you encountered this idea of decomposition. Early in high school, when studying basic algebra, you learned that if we have a polynomial, like say x squared minus 1, we can often factor, or if you like, decompose, it into a product of simpler, more fundamental parts. In this case, we have boiled it down to irreducible linear factors, x minus 1 and x plus 1. All that is very familiar, and now here you are a few years later studying linear algebra. And there are a number of places in linear algebra where it can be useful, when we have some matrix, to decompose it, or factor it if you like, into some sort of product of simpler or more fundamental, or just simply revealing matrices. So this is really just continuing the themes you've encountered going all the way back to elementary school. And there are various famous sorts of matrix decompositions out there, but the one, of course, we are talking about today is the so-called eigendecomposition of a matrix. And I think what I'd like to do to introduce it is just to write down an example of what an eigendecomposition looks like, and then we can discuss where it comes from, why it works, when it works, and so on. Hang on one second. I need to do a little intervention here. While editing this video, I realized that there is something I should have mentioned before you see your first example of an eigendecomposition. Because no doubt you will wonder, okay, he just factored a matrix, but how did he figure out those factors? So I want to tell you right here at the outset that except for in the simplest cases, one usually finds an eigendecomposition of a matrix with a computer. You will want to know how to interpret it and what it's doing under the hood, but that's where they typically come from. If you're a computer programmer, you might write your own program to do such a thing, or you might incorporate some sort of package that already includes the possibility of doing this. And if you're not, you might use existing software, or if the matrix is relatively small, a calculator that you can find on the web, like this one at matrixcalculator.org. And I just want to show you what this looks like in practice. Down here in the blank matrix A, I will fill in entries like so, and now we have the good old-fashioned telephone matrix. And you'll notice all these buttons down here where it says more, diagonal matrix, Jordan decomposition, matrix exponential, singular value decomposition. Well, never mind the matrix exponential. The other three all actually are various different types of decompositions of our matrix A. The one that says diagonal matrix, that will actually give us the eigendecomposition, because as I said, the process of diagonalization really does produce the eigendecomposition. So let's go ahead and push that button now. And look at what pops up down at the bottom. Our telephone matrix has been factored into a product of 3 matrices, the middle one of which is a diagonal matrix. And this is indeed an eigendecomposition of the telephone matrix, as easy to obtain as pushing a button. But what does it mean? That's what we're going to talk about next. So I will bring my little intervention to an end. And now we will go back to, well, to myself, a very innocent version of myself who has no idea that he is being interrupted like this. But anyway, I hand the mic back over to you, ever so slightly younger version of myself. So here we go. Here comes your first eigendecomposition. Let's start with this matrix A, whose rows are 3, 4, and -1, -2. And I am going to decompose it into a product of 3 matrices, namely these 3 matrices. And if you care to multiply them together, you'll see that you will indeed recover A. Well, okay, you might think, I've decomposed A into a product of three matrices. That takes care of the decomposition part, but what's so eigen-y about this? What makes this an eigendecomposition? What makes this something that is actually revealing facts about matrix A that I don't know just by looking at A? Well, I will tell you. Let's start with the middle matrix in the decomposition, since that's the one that no doubt attracts your attention first. It attracts your attention because it is a diagonal matrix, and I spent the beginning of this video praising diagonal matrices to high heaven. Every eigendecomposition breaks a matrix A into a product of three factors, the middle one of which is diagonal, and more importantly, the entries on the main diagonal are the eigenvalues of the matrix we have decomposed. So just by looking at this eigendecomposition of A, we immediately know A's complete set of eigenvalues. 2 and -1. Well, that's pretty good. But wait, there's more. Let's look at the first of the three matrices in our eigendecomposition. Its columns tell us something important. They constitute an eigenbasis for, in this case, R2, since we're dealing with a 2 by 2 matrix, relative to our matrix A. Oh, that's very nice indeed. And since we can, we might as well go ahead and verify this. Clearly, these two vectors are linearly independent, so they do constitute a basis for R2, but are they an eigenbasis relative to our given matrix? Well, let's see. Let's come down here and do a little quick scratch work. If we take the matrix vector product A times -4, 1, the first column of that first matrix in the decomposition, we will get, as you can verify, -8, 2, which is indeed 2 times our input vector -4, 1. So yes, -4, 1, our first column there, really is an eigenvector relative to A. And notice the eigenvalue of 2, which of course appears in our diagonal matrix. And it is no accident that the first column, that first eigenvector, has as its eigenvalue the first entry in the diagonal. The eigenvectors and eigenvalues will always match up that way in an eigendecomposition. Similarly, if we were to compute A times -1, 1, the second column in the first matrix in our decomposition, we end up with 1 -1, which of course is -1 times our input vector, -1, 1. So yes, -1, 1 is an eigenvector, and its corresponding eigenvalue is -1. Well, that's terrific. Now we can start to see the value of an eigendecomposition. It's like an interesting X-ray of our matrix. If we have an eigendecomposition, it exposes to view the eigenvalues of the matrix and an eigenbasis. What more can a person ask for? Well, one thing you might ask is, what about this matrix on the right, the ugly one with fractions in it? Does that show me anything interesting? Well, not as interesting as the first two matrices, but it does bear an important relationship to the first matrix. And you may well have guessed what that relationship is based on some things we have talked about already in this video. Namely, those two matrices are inverses of one another. If you go through the usual operations to invert that left matrix, you'll see that this is so. And all of what we have seen in this particular example of an eigendecomposition occurs in every eigendecomposition. And if we want to talk about eigendecomposition in the abstract, not just for one particular matrix, we would usually describe it in the following sorts of symbols. We take some matrix A and decompose it, of course, into a product of three matrices, and the middle matrix we usually describe, when we're discussing it in the abstract, with this symbol. That is a capital lambda. We tend to use that symbol because we know that middle matrix is going to be our diagonal matrix that contains A's eigenvalues. And as you will recall, the typical symbol for an eigenvalue is a lowercase lambda. We tend to write the usual equation defining an eigenvalue, for example, as T of V equals lambda of V. That's the scalar by which our eigenvector is being stretched. Anyway, the first matrix in the eigendecomposition is often, though not quite so universally, symbolized by a capital V. The reason for this is that if the middle matrix contains the eigenvalues, the first matrix contains eigenvectors, a whole eigenbasis full. And then, of course, the third matrix would be written as V inverse, since the outer matrices, as we said, are inverses of one another. These symbols are not quite universal, but they're very common, especially the capital lambda for the middle diagonal matrix containing the eigenvalues. And of course, when we write it this way, we immediately think of what we were talking about a little while ago. Similar matrices, because when we eigendecompose A into this product of three matrices, we see that A is similar to the diagonal matrix full of A's eigenvalues, lambda. Lambda and A represent the same linear transformation, just according to different bases. If we're thinking of A as the representation of a map according to the standard basis, then lambda is the representation of the same map according to the eigenbasis given by the columns of V. And when we have an eigendecomposition like this, one nice consequence is that it becomes very easy to take powers of the given matrix that we have eigendecomposed. And you might say, well, wait a second. I understand why it's easy to take powers of the diagonal matrix, but to take powers of A, I have to take powers of this product of three matrices. And two of those three matrices are not diagonal, so isn't this just making life a little harder, at least as far as raising a matrix to a higher power goes? Not so, not so. I will show you why. Let's say we have an eigendecomposition, the one described here, and we want to raise the given matrix A to some power k. Well, that means that we are raising the product V lambda V inverse to the kth power, which is this huge product, V lambda V inverse, V lambda V inverse, V lambda V inverse, and we keep multiplying V lambda V inverse k times. But wait, this simplifies considerably, because look at our gigantic matrix product. We know matrix multiplication is associative because function composition is associative, as we noted way back in chapter 3. So that means I could insert parentheses wherever I want. For example, right here, and I get V inverse V. Well, what's the product of V inverse V? Obviously, the identity matrix, which just gets absorbed into the overall product. Same thing with this V inverse V. Same thing with this V inverse V. Same thing with this V inverse V, all the way down. All those V inverse V's collapse. And think about what survives the slaughter. Well, the initial V, which doesn't have a V inverse mate, that lives on. The lambda is still around, the first one. The second lambda is still around. The third lambda is still around. All the way down until the last, the kth lambda. So that means we are going to get k lambdas in a row, all the intervening V and V inverses having canceled each other out. And then finally at the end, we get a V inverse that doesn't cancel because it doesn't have a V following it. So we have V inverse. And at the end of the day, A to the kth power is V times lambda to the kth power times V inverse. And look what's happened. Lambda is diagonal, so raising it to the kth power is a piece of cake. Once we've done that, we just have two matrix multiplications to do. V times lambda to the k, which is especially easy since lambda to the k is itself diagonal. And then that product has to be multiplied by V inverse. So there's really only two multiplications of matrices that have to take place, as opposed to k minus one of them over here. So if you're raising a matrix to any substantial power, and especially if your matrix itself is fairly large, eigendecomposition is exactly what you want, if you can get one. Remember, you can only get an eigendecomposition of a matrix A if there is an eigenbasis relative to A. If you don't have one, obviously you can't have an eigendecomposition. But if you have one, oh, it makes life much, much easier. In fact, let's do a quick example with this concrete matrix that we have right here, moved up, so have a little room. So let's take this matrix A and raise it to the 10th power. Now, you really don't want to take this matrix, multiply it by itself, multiply the product by this matrix again, multiply that product by this matrix again, multiply that product by this matrix again, and so on and so forth. It would be utter tedium and it would take a long time. But since we have the eigendecomposition, raising A to the 10th is not that hard, because we know what it's going to look like, according to what we just discussed over here, is going to be the 10th power of the middle matrix, the diagonal one, bookended by the two other matrices. So A to the 10th here will look like this stuff. The left matrix times the diagonal matrix to the 10th times the right matrix. And as we discussed earlier in the video, raising a diagonal matrix to the 10th power is as easy as raising each of its components on the main diagonal to the 10th power. So when we do that, we get 2 to the 10th and minus 1 to the 10th on the diagonal. 2 to the 10th is 1024, and minus 1 to the 10th, of course, is 1. And now this isn't hard at all. It's just a couple of matrix multiplications. I'll leave it to you to carry them out if you want to. When you do, you should end up with this matrix, assuming I still know how to do arithmetic, which I sometimes doubt. And so much for eigendecomposition. Remember this main form and what it tells you. The middle matrix lambda is diagonal and it stores A's eigenvalues. The left matrix V stores an eigenbasis with respect to the given matrix A. And the right matrix is mostly just along for the ride. It's the inverse of the left matrix. But seeing that pair of inverses surrounding the diagonal matrix reminds us that the diagonal matrix is just another representation of the same map represented by A. It's just that as capital lambda, it is represented by the eigenbasis whose columns appear in matrix V. I should add here at the end that in most treatments you will see of eigendecomposition, if you look one up online, there's no mention made of change of basis or anything like that. It's happening, of course, under the hood, but it's often described in purely algebraic terms, which is efficient, but I think understanding what's happening in terms of change of basis helps us really understand why an eigendecomposition is a natural thing and not just some weird thing that falls out of some arcane algebra. So maybe to run through it one last time, now that you know what it is, will help pull everything together. Suppose we have some square matrix A. It has to be square because we can only talk about eigenstuff of square matrices, because a square matrix corresponds to a linear map from a space to itself, and we have to have a map like that if we're going to talk about, say, an eigenvector. If we're mapping one space into a totally different space, obviously the result can't be a mere stretch. We'd be sending the vector to a totally different reality. But anyway, we're supposing we have a square matrix so that we can talk about eigenstuff, and that moreover, our square matrix admits an eigenbasis, which I'll call B, which consists of the vectors v1, v2, up through vn. These are our linearly independent eigenvectors, each of which, of course, corresponds to a particular eigenvalue, and I will call those eigenvalues lambda 1, lambda 2, all the way down to lambda n. So we know that A times v1 is lambda 1 v1, or A times v2 is lambda 2 v2. Okay, so we have such a square matrix. There's an eigenbasis with respect to it. We have names for the eigenvectors and eigenvalues. We can think of that square matrix A as the standard representation of some linear map T, since we can do that with any matrix, as we discussed earlier. But since A has this eigenbasis, we know it is diagonalizable. And in fact, we know that if we represented the map T with respect to basis B, we would get a diagonal matrix, of course. The first column, for example, would be the image of v1, the first vector in the basis, expressed in B coordinates. Well, we know what T does to v1. It's an eigenvector, v1 is, with eigenvalue lambda 1. So T of v1 is lambda 1 v1. Now we just have to express that in B coordinates. How many v1 steps, v2 steps, etc. do we have to take to get to lambda 1 v1? Well, the answer is obvious. Once we take lambda 1 v1 steps, we're there already. So we don't take any v2 steps or v3 steps or anything else all the way down to vn steps. And as we have detailed several times now already, something similar happens for the second column, where we need the image of v2 under the map expressed in B coordinates. Well, the image of v2 is lambda 2 v2, so we have to express lambda 2 v2 in B coordinates. We get to lambda 2 v2 by taking no v1 steps, lambda 2 v2 steps, and no steps of any other kind. And the same thing happens all the way down. And so yes, our representation of T relative to the basis B, this eigenbasis, is indeed diagonal. And moreover, all the eigenvalues of the map appear on that diagonal. So since A, our given matrix, and this guy, our diagonal matrix, which we will call capital lambda, are both representations of the same underlying map, A and lambda are similar matrices. That means that we should be able to get from one to the other by surrounding either of them with just the right pair of change of basis matrices. In fact, we can write down how that would work very easily. Matrix A describes how to carry out this linear transformation T in English, as it were, in basis E. Matrix lambda, our diagonal matrix, describes how to carry out the same transformation T, but in this different language, in language B, in Bulgarian. So we need our change of basis matrices to act as translators. And what will the change of basis matrices look like? Well, presuming that these vectors we have right here, the vectors of our eigenbasis, are expressed in standard coordinates, then if I were to make a matrix consisting of those vectors as its columns, these would be the vectors in basis B expressed in standard coordinates, E coordinates. So this would be, based on our work in chapter 6, the B to E change of basis matrix. Let's give it a name, like vector V. All right, well in that case, we know something about V inverse. If V is the B to E change of basis matrix, its inverse, obviously, is the E to B change of basis matrix. And now we have all the ingredients to write down the relationship between A and lambda. Namely, A, T's representation with respect to the standard basis, can be achieved as follows. V times capital lambda times V inverse. Because V inverse is the E to B change of basis matrix. So if you feed in a vector in standard coordinates, V inverse changes it to B coordinates, which then passes it on to capital lambda, which loves B coordinates because it is the matrix representation of linear map T relative to B coordinates. So our original vector in E coordinates gets translated to B coordinates, then lambda sends it to T of V's B coordinates, which V, being our B to E change of basis matrix, turns into T of V's standard coordinates. So the net effect is that when a vector's standard coordinates go in, what comes out are the standard coordinates of that vector's image under T. In other words, what all this does at the end of the day is simply carry out the linear map T in standard coordinates. And that, of course, is what A does, which explains this equality. All right, so there's a lot going on there, but hopefully this gives you a feel for why, when we have an eigendecomposition, that middle matrix is diagonal, consisting of the eigenvalues of the original matrix, and the leftmost matrix has as its columns the corresponding eigenvectors. And finally, it explains why the rightmost matrix in our eigendecomposition is simply the inverse of the leftmost matrix. The two of them surround the middle matrix, thus carrying out a change of basis. And if you feel like I have just been saying the same thing over and over in this video in lots of different ways, I hear you. I have been saying the same thing over and over in this video. But these are important ideas, and it takes a while to get used to them, so I think they bear repetition. Maybe the last thing I should say is that if we wanted to understand how a computer creates an eigendecomposition in very broad terms, the answer is now fairly straightforward. It has to come up with an eigenbasis relative to that matrix, and then for each vector in the eigenbasis, come up with the respective eigenvalue. Once it has those, it stores those eigenvalues in a diagonal matrix, stores the eigenvectors from the basis in another matrix with those as its columns, inverts that matrix, and that is the matrix that appears on the right. But we've just pushed the problem down the road. What is the computer doing? How do we actually find an eigenbasis for a given matrix, for a given map? Well, we will discuss that next time. Now that you know all about eigenvalues and eigenvectors and eigenbases and eigenspaces and even eigendecomposition, now the time has come to discuss how we actually find such things when they aren't given to us. So that is the topic of the next lecture. It is time at last to bring this one to an end. So let's do that.